High above us, in the vast expanse of our solar system, shines a celestial object of immense fascination: Mars. Known as the Red Planet, Mars has captivated humanity for centuries. Its fiery hue, visible even to the naked eye, has sparked countless myths and legends. Ancient civilizations associated Mars with war and bloodshed, while science fiction writers imagined it as a world teeming with alien life. But what is it about Mars that makes it so red? This intriguing question has puzzled scientists and stargazers alike for generations. The answer lies in the composition of Mars's surface. Unlike Earth, with its lush green landscapes and blue oceans, Mars is covered in a fine layer of dust and rock. This material contains a high concentration of iron oxide, the same compound that gives rust its reddish-brown color. Over millions of years, the iron on Mars's surface has reacted with oxygen in the atmosphere, forming a thin coating of rust. This rusty layer is what gives Mars its distinctive red appearance. The redness of Mars is not merely a cosmetic feature, it holds valuable clues about the planet's history and evolution. By studying the composition and distribution of iron oxide on Mars, scientists can piece together the planet's past climate, geology, and potential for harboring life. Join me as we delve deeper into the science behind Mars's rusty facade and explore the secrets it holds. Iron oxide, the chemical compound responsible for Mars's striking red color, is ubiquitous on our planet as well. This compound, which is a result of the oxidation process, can be found in various forms and locations, from the smallest speck of dust to the largest structures made of iron. We encounter it every day in the form of rust. Rust is not just a nuisance that weakens metal structures, it is a fascinating chemical phenomenon that tells a story of interaction between elements. Rust forms when iron or an alloy that contains iron such as steel is exposed to oxygen and moisture for an extended period. This process can take days, months, or even years, depending on the environmental conditions. The oxygen molecules interact with the iron atoms, creating iron oxide, which is more commonly known as rust. This interaction is a slow but relentless process that gradually transforms the surface of the metal. This process, known as oxidation, is a chemical reaction that involves the transfer of electrons. In a controlled environment, scientists can demonstrate how oxidation works and study its effects on different materials. When iron is exposed to oxygen, it loses electrons while oxygen gains electrons. This electron exchange is fundamental to the formation of rust and is a key concept in understanding chemical reactions. This exchange of electrons forms iron oxide, a stable compound that is reddish-brown in color. The color and texture of rust can vary depending on the specific conditions under which it forms. The presence of water accelerates the oxidation process, acting as an electrolyte that facilitates the flow of electrons between iron and oxygen. This is why rusting is more prevalent in humid or wet environments. On Mars, the process of oxidation has been occurring for billions of years, transforming the planet's surface into a vast, rusty expanse. The red color of Mars is a testament to the planet's long history of exposure to oxygen. The thin atmosphere of Mars, composed primarily of carbon dioxide, contains trace amounts of oxygen. Despite the low concentration, this oxygen has been enough to cause significant oxidation over geological timescales. While this small amount of oxygen is not enough to support life as we know it, it has been sufficient to react with the iron-rich rocks and dust on Mars, creating the planet's distinctive red hue. This reaction has painted the Martian landscape in shades of red and brown. The abundance of iron oxide on Mars tells us that the planet was once much wetter and warmer than it is today. Ancient riverbeds and lake beds provide evidence of a time when liquid water was abundant on the Martian surface. Liquid water, essential for the formation of rust, is thought to have existed on Mars's surface billions of years ago. This water would have interacted with the iron in the rocks, leading to widespread oxidation. Evidence suggests that ancient rivers, lakes, and perhaps even oceans once flowed across the Martian landscape, providing the necessary conditions for widespread oxidation to occur. These ancient waterways have left their mark on the planet, shaping its surface and contributing to its iconic red color. Rust, while often perceived as a nuisance on Earth, is a treasure trove of information for scientists studying Mars. This seemingly mundane process of oxidation holds the key to unlocking the mysteries of the red planet's past. The presence, distribution, and composition of iron oxide on the red planet provide valuable clues about its past environment and potential for habitability. By studying these iron-rich soils, scientists can piece together the climatic and environmental conditions that once prevailed on Mars. One of the key insights that rust provides is about the history of water on Mars. The ancient riverbeds and dried lake beds suggest that liquid water once flowed across the Martian surface, carving out channels and leaving behind telltale signs of its presence. As mentioned earlier, liquid water is essential for the formation of rust. This means that the extensive iron oxide deposits on Mars are direct evidence that water once existed there in significant quantities. The fact that Mars is covered in iron oxide suggests that the planet was once much wetter than it is today. These vast rusty terrains are a testament to a time when Mars had abundant water, which played a crucial role in shaping its landscape. Scientists believe that billions of years ago, Mars had a thicker atmosphere and a warmer climate, allowing for the existence of liquid water on its surface. This ancient Martian environment could have been similar to early Earth, potentially supporting microbial life. The type of iron oxide present on Mars can also tell us about the planet's past climate. Different forms of iron oxide, such as hematite, can indicate varying environmental conditions, from wet and humid to dry and arid. For instance, the presence of hematite, a specific type of iron oxide, suggests that Mars may have experienced periods of aridity, with water evaporating and leaving behind mineral deposits. These minerals are like time capsules, preserving the history of Mars' climate changes. Hematite is often found in areas where water has evaporated, such as dry lake beds. This mineral provides a snapshot of the environmental conditions that existed when the water was present and then disappeared. Moreover, the study of rust on Mars can help us understand the planet's geological processes. By examining the distribution and composition of iron oxide, scientists can infer the history of volcanic activity, erosion, and sedimentation on Mars. The distribution of iron oxide can reveal patterns of erosion, sedimentation, and volcanic activity. These processes have played a significant role in shaping the Martian landscape over billions of years. By analyzing the different layers of rust, scientists can reconstruct the geological history of Mars and gain insights into how the planet's surface has changed over time. Each layer tells a story, revealing the dynamic and ever-changing nature of Mars's environment. Section 4. Robotic Explorers on Mars, Perseverance and Curiosity. To unlock the secrets held within Mars's rusty exterior, space agencies worldwide have dispatched a fleet of robotic explorers to the Red Planet. Among the most sophisticated and successful of these missions are NASA's Perseverance and Curiosity rovers, which have been tirelessly exploring the Martian surface, collecting data, and sending back breathtaking images. Perseverance, the latest and most advanced rover to land on Mars, touched down in February 2021. Its primary mission is to search for signs of past microbial life, explore the planet's geology and climate, and collect rock and soil samples to be returned to Earth for further analysis. Curiosity, Perseverance's predecessor, has been exploring Mars since 2012. This car-sized rover has made groundbreaking discoveries, including confirming the presence of ancient lakes and rivers on Mars and finding evidence of organic molecules, the building blocks of life. Both rovers are equipped with a suite of scientific instruments designed to study the Martian environment in detail. Among these instruments are spectrometers, which can analyze the composition of rocks and soil, including the different types of iron oxide present. By studying the composition and distribution of iron oxide, these rovers are helping scientists piece together the history of water and climate on Mars. Section 5. Digging deeper insights from Martian rovers. In this chapter, we delve into the groundbreaking discoveries made by the Perseverance and Curiosity rovers, which have significantly advanced our understanding of the Red Planet. The Perseverance and Curiosity rovers have revolutionized our understanding of Mars's rusty surface. These robotic explorers have traversed the Martian terrain, conducting experiments and sending back invaluable data. Their findings have provided unprecedented insights into the planet's past environment and its potential for harboring life. By analyzing soil samples and rock formations, the rovers have uncovered clues about Mars's geological history. One of the key discoveries made by these rovers is the presence of hydrated minerals, which are minerals that contain water molecules within their crystal structure. This discovery has profound implications for our understanding of Mars's history. These hydrated minerals suggest that liquid water once existed on Mars's surface for an extended period. The presence of water is a crucial factor in the search for past life on Mars. The presence of hydrated minerals suggests that liquid water once existed on Mars's surface for an extended period. This water would have interacted with the iron-rich rocks, leading to the formation of iron oxide and the rusty color we observe today. This water would have interacted with the iron-rich rocks, leading to the formation of iron oxide and the rusty color we observe today. The discovery of these minerals has provided a window into Mars's wetter past, leading to the formation of iron oxide and the rusty color we observe today. Curiosity, for instance, discovered hydrated minerals in the Gale crater, suggesting that the crater was once a lake or a series of lakes billions of years ago. Curiosity, for instance, discovered hydrated minerals in the Gale crater, suggesting that the crater was once a lake or a series of lakes billions of years ago. This finding has reshaped our understanding of Mars's climatic history, suggesting that the crater was once a lake or a series of lakes billions of years ago. Furthermore, the rovers have found evidence of different types of iron oxide, each indicating a different environment in Mars's past. Furthermore, the rovers have found evidence of different types of iron oxide, each indicating a different environment in Mars's past. For example, the presence of hematite, a mineral that forms in the presence of water, suggests that Mars may have experienced periods of aridity, each indicating a different environment in Mars's past. For example, the presence of hematite, a mineral that forms in the presence of water, suggests that Mars may have experienced periods of aridity, with water evaporating and leaving behind mineral deposits. For example, the presence of hematite, a mineral that forms in the presence of water, suggests that Mars may have experienced periods of aridity, with water evaporating and leaving behind mineral deposits. The rovers have also detected the presence of goethite, another type of iron oxide that forms in the presence of water and oxygen. A mineral that forms in the presence of water suggests that Mars may have experienced periods of aridity, with water evaporating and leaving behind mineral deposits. The rovers have also detected the presence of goethite, another type of iron oxide that forms in the presence of water and oxygen. Suggests that Mars may have experienced periods of aridity, with water evaporating and leaving behind mineral deposits. The rovers have also detected the presence of goethite, another type of iron oxide that forms in the presence of water and oxygen. The discovery of goethite suggests that Mars may have once had a more oxygen-rich atmosphere than it does today, with water evaporating and leaving behind mineral deposits. The rovers have also detected the presence of goethite, another type of iron oxide that forms in the presence of water and oxygen. The discovery of goethite suggests that Mars may have once had a more oxygen-rich atmosphere than it does today. The rovers have also detected the presence of goethite, another type of iron oxide that forms in the presence of water and oxygen. The discovery of goethite suggests that Mars may have once had a more oxygen-rich atmosphere than it does today, another type of iron oxide that forms in the presence of water and oxygen. The discovery of goethite suggests that Mars may have once had a more oxygen-rich atmosphere than it does today. This finding has significant implications for our understanding of the planet's potential to support life. The discovery of goethite suggests that Mars may have once had a more oxygen-rich atmosphere than it does today. The findings from these robotic explorers have painted a more complex and intriguing picture of Mars's past, suggesting a planet that was once much more Earth-like than previously believed. The findings from these robotic explorers have painted a more complex and intriguing picture of Mars's past, suggesting a planet that was once much more Earth-like than previously believed. These discoveries have opened up new possibilities for future exploration and the search for life beyond Earth, suggesting a planet that was once much more Earth-like than previously believed. As we continue to explore Mars, each new discovery brings us closer to understanding the mysteries of our neighboring planet and the potential for life beyond Earth.